Hello everyone, my name is Steve Nesbitt from the University of Illinois, and today I'm going to be presenting on an ongoing collaboration between partners here at the University of Illinois, University of Buenos Aires, University Nacional de Córdoba, and the provincial government and agencies within the provincial government of the Province of Córdoba in Argentina. This project is a collaboration that's an outgrowth of the RELAMPAGO Field Campaign that was conducted in 2018 and 2019, where we're hoping to improve forecasts for extreme rainfall events to improve water management within the reservoirs and streams within the province of Córdoba. And before I get started, I want to acknowledge funding from the National Science Foundation in the U.S., as well as the provincial government within the province of Córdoba in Argentina. The Sierras de Córdoba are a mountain range located in central Argentina, about 500 kilometers east of the main Andes Cordillera. This mountain range reaches up to about 2,500 meters tall, is about 500 kilometers long, and is located in a region where the South American low-level jet transports copious low-level moisture into this region during the spring, summer, and fall seasons. This low-level moisture, coupled with the upper-level jet that passes over this region in the southern hemisphere, leads to strong instability and shear, leading to very organized convective systems. These systems can range from isolated supercell thunderstorms with very heavy instantaneous precipitation rates up to huge mesoscale convective systems with very wide convective cores. The result, in terms of hydrology, is that combined with the steep slopes in this region, very, very intense flash flooding can happen. And down here below, you see a couple examples here where on the left, you see very rapid rise flash flooding associated with a convective storm in the Sierras, as well as down here on the lower right, very intense flash flooding along the Rio San Antonio within the central Sierras, where you have these rivers which are very much enjoyed by the local population, flooding very quickly and flooding homes, businesses, and even leading to loss of life in this region. And so within this region where you have these very intense flash flooding regions, you also have a very valuable water resource from the warm season rainfall that occurs during this period. And so the challenge here is to make sure that much of this runoff, as much as possible, is captured by the local reservoirs that exist within this region. So zooming in on this region, we see the Sierras de Córdoba indicated here within the topographic shading. The major city of Córdoba is located within one of the basins that runs out of the Sierras, as well as smaller cities and much more distributed development areas within this area, which are very popular tourist destinations for people in the region. Within this region, the local rivers have dozens of dams and reservoirs located within the terrain. And these reservoirs collect this heavy rainfall that runs off these steep slopes and attempts to preserve the water resources for tourism, as well as agricultural uses, as well as hydropower generation. And so the challenge here, of course, is that all this warm season rainfall is desired to be captured by these reservoirs. And conversely, during the dry season, during the winter, there's almost no precipitation. And so these reservoirs form really the basis of much of the local economy, from tourism to agriculture. So it's really important for the water resources to be maximized in this region for the population. The local flash flooding within this region is well known to the local hydrologic community, and extensive resources have been deployed to alert the local public for this flash flooding. And there's extensive monitoring of many meteorological variables and hydrometeorological variables within this region. Here's an example of some local observations that were taken during the RELAMPAGO Field Campaign of one of these floods, showing the very rapid rise of the floodwaters and the potential dangers to locals who might be enjoying the river along its banks. Some of the assets that are deployed within this region to monitor flash flooding include a local mesonet, with real-time data distribution to the hydrologic centers within the province, real-time flood forecast models that take observed precipitation and, based on historic rating curves, predict the runoff and potential for flooding within the region, and this tool is available to the public, as well as dam prediction models that help predict the level of the reservoirs within the region. In addition, in 2015, a dual polarization radar was installed within the city of Córdoba, located here, that helps provide real-time QPE information that could be potentially used for flood monitoring. So the RELAMPAGO Cacti Field Campaign, which was conducted in late 2018 and early 2019, had hydrometeorology as a focus, and it also provided the opportunity for the field campaign participants from the U.S. and Argentina to integrate with the hydrologists within the local area of the Sierras de Córdoba. The hydrometeorological component of RELAMPAGO Cacti focused on a lot of issues that helped the local hydrologists, which were embedded within the campaign, as well as increased the communication between the atmospheric scientists and those that can understand the processes behind heavy rainfall, as well as those that actually deal with the impacts of this heavy rainfall. And so it established a strong end-to-end partnership in improving the resilience of the Sierras de Córdoba to heavy rainfall. And so within RELAMPAGO, we had copious atmospheric observations of multi-scale phenomenon using radars, atmospheric soundings, in situ surface sensors, flux towers, lightning observations to help understand the convective systems within this region. And then we had streamflow observations and other soil moisture sensors within a broader hydrometeorological network to help us understand how the whole process happens between atmospheric moisture, precipitation, runoff, flooding, and changes in the land surface characteristics. So the deployment of mobile assets for the RELAMPAGO Field Campaign necessitated the development of a convection-permitting model ensemble for us to be able to predict the location and timing of convective events within the province of Córdoba. This ensemble turned out to be quite useful for hydrologic prediction and really opened the eyes of the local hydrologic community that local precipitation prediction was actually possible at the basin scale within the Sierras de Córdoba. And so this information was found to be much more useful than the global models which exist within this region, and added to local modeling capabilities within the Servicios Meteorological Nacional, the National Weather Service in Argentina. And so as a result of the campaign, we've developed tools for model runs to be ingested into the local hydrologic office, such that this information can be used for hydrologic prediction. So here's an overview of the ultimate procedure that we'd like to be able to do, tracing rainfall forecasts to flow discharge in the rivers, ultimately to the dam evolution and the management of the dam. Of course, the dam management depends on the time of year. If you're early in the rainy season, you can be a little bit more aggressive in sort of managing the levels. Towards the end of the rainy season, we want to make sure that the ultimate level stays near the spillway so that the maximum amount of water resources is maintained. And so through the forecast procedure and ultimately through the predictions, different tools are used depending on the uncertainty of the ultimate inputs. So currently 2 different models are run. With longer lead times, we take forecasts from the convection permitting models, put them into the flow distributed model to predict the hydrographs and different management aspects, and then ultimately the ultimate levels of the reservoir are predicted, and of course then you have both the uncertainty of the precipitation and the runoff. Then at shorter time scales, when we have observed precipitation, we use rating curves to then predict the hydrographs from the observed precipitation from the rain gauge network, and then that is used at short terms to try to predict the dam evolution. So here's an example from a recent flood at the San Roque Dam, which is near Carlos Paz, Argentina. Here on the left, we have the predicted precipitation from the WRF model over 24 hours. And you can see that the model was putting out in excess of 80 millimeters of precipitation. That model information was passed into a GIS tool, which then was input into the rainfall runoff model, and the flows of the into the San Roque Reservoir were predicted. And on the upper right, here's a simulation with 2 of the 2 valves open at 100% in terms of the level of the reservoir. Now note briefly that the reservoir was not lowered prior to the event because they really want to maintain the flow at the level of the spillway. And then you can see the forecast precipitation here, 56 millimeters for 24 hours. So once we get shorter term forecasts, we have observed precipitation, and that information can be fed into a shorter term model using that input precipitation. And what you see is that the WRF model simulation shown on the previous slide and the observed precipitation agree quite well, which is good. It shows that the model did have some skill in predicting the evolution with 24 hours notice. And now here's the results from once the floods are actually observed, running the pulse model with the inputs into the reservoir shown here, the total flow in and then the flow out, and then on the right you see the pulse model prediction of the reservoir level. And again, you see it's pretty consistent with the prior forecasts, and which shows that during this extreme event we're able to manage the reservoir with a lot of certainty. So in total you see a lot of consistency here. Clearly the WRF model was a little bit underdone in terms of the levels. However, it did provide a useful tool to provide an overview with 24 hours notice in this particular case. In addition, tools are available to run hydrodynamic models to look at the flows within the reservoir. And so you can see, for example, here are some tools to be able to understand the impacts of flooding near the reservoir. And here a simulation of the actual level of the reservoir and kind of show what areas will be impacted, and that information can be sent to local stakeholders. But overall, if you compare a lot of the different model runs that were run for this particular event, the San Roque Reservoir is here on the top, and here on the left you see the observed average precipitation in the basin was 66 millimeters. You see two of the models, one of the ensembles from the local hydrologic agency and the WRF model from the UIUC were within 1 millimeter, which offered pretty good skill. The global models were much lower, and even the Weather Service model in Argentina was low, so that the local models provided by WRF got this particular event quite well. Satellite precipitation estimates were way too high and way too low, respectively, so they generally don't provide a lot of skill. But the WRF model seems to provide a lot of value here across these different reservoirs. In addition, long-term forecasts are used in reservoir management, and so we can use an ensemble of global models to try to look at longer-term variability and for longer-term seasonal to subseasonal reservoir management, and this is an area of active research. And so here we can start to look at the seasonal cycle and try to predict, based on sort of climatological conditions, you can try to anticipate longer-term precipitation variability based on forcing from things like MJO and El Nino. So just to wrap up, this partnership that arose from the RELAMPAGO Cacti Field Campaign has married both atmospheric scientists and hydrologists to work together to try to improve reservoir management in this region. The short-term water management has really improved through the use of convection-permitting forecasts, even in the warm season, where predictability is quite low, and it allows the local managers to anticipate extreme events so that those can be mitigated. Of course, we have a lot of work to do in terms of statistical validation, which we'll continue to do as we go forward. Also, long-term seasonal to subseasonal forecasts are possible and show some promise in maintaining the reservoir levels. And we hope to continue this collaboration to establish the uncertainty and inclusion of advanced tools like distributed hydrologic modeling, such as WRF Hydro. And a recent paper by Sujan Paul, one of the former students here at Illinois, used this to demonstrate the skill in using ensembles to predict accurate hydrological prediction. So we'll stop there and look forward to any follow-up after this conference. Thank you.